start with a review of the electrical events of the cardiac cycle. And since you're right here, will you tell me the first step in the electrical cycle of the heart?
You want like SA node activated, you want me to just like the atria? All right, the atria activated.
So we start with the SA node, and then the atria become activated, and that results in the P wave. This should be reviewed from Jake last week, but just to go over really quickly. Derek, what happens after that?
The AV node activates.
Yep. And then Tanner, what happens after that?
Then you're going to go into the bundle of his.
Yep. Jake, what happens after that?
Left and right bundle branches.
Yep. So then that's the start of our QRS, is as it goes down the septum or Purkinje fibers. And I'm going to call on you next.
That was the Purkinje afterwards.
Yep. And then what happens after the Purkinje?
After Purkinje activated, well, you get contraction, and then after that, you get repolarization.
No, but what happens is, how do we get from the Purkinje to all the other many more time cells? I think we talked about this last week.
Yeah, we glossed over this detail.
Yeah. So you imagine a bunch of fibers, and they're sort of terminated. And somehow those fibers then become the initiating sites into what's called the working myocardium. And it turns out there are specialized coupling cells between the two. So there's Purkinje and it's working, and then there's these, what do we call them? There's a generic name for them, but they're basically specialized cells that couple between the two areas and ensure that you get, solid coupling and successful excitation of the working myocardium. What it means, if you think about it, if you're able to measure all the sites in the ventricles where the heart excites, you'd expect there to be a lot.
I mean, I'd assume there'd be a lot of sites of activation because you want to activate everything together.
Well,
more or less.
whether you want to or not, that's that's teleological thinking. But the reality is there's this very, very distributed network of Purkinje fibers. Each one of them initiates some activation in the nearby region. So there's an enormous number of individual sites that are all being stimulated whenever excitation reaches the end of those fibers, in a sequence that is more or less synchronized, because the nature of those Purkinje fibers is very rapidly spreading excitation.
And you raised your hand.
Yeah, I was just going to ask, I know we talked about, that was like a good lead in on a cellular level. The cells are different, like the Purkinje fiber is very different from myocyte. And now you said there's a coupling. Anatomically, like we always look at least in my experience, so we've looked at diagrams when we look at the electrical activity of the heart. Can you see, like the SA node, the AV node, can you see that? Is there a visible difference between the tissue?
If you extract cells from those regions, look at them under a microscope, then some of them definitely will look different from others. The working myocardial cells different from Purkinje cells. In many ways, actually. Purkinje cells, for example, have no contractile proteins.
Okay.
And so have you ever seen a muscle cell? Yeah, so it has these.
Yeah.
Like, where would the contractile proteins be in that?
I mean, there's like a lot of contractile proteins.
Right.
Or you mean like macroscopically they make like fibers align? Is that what you mean?
Well, no, I mean the individual cells. So if you took a Purkinje cell and a working myocardial cell and stared at them side by side under the microscope, they would be dramatically different because those contractile proteins create this sort of stripe pattern within the cell. Right? There's all these called sarcomeres, and they have structure level. And the Purkinje cells don't actually have those. And another key feature of the cellular domain that the working myocardial cells have is a set of what are invaginations. They're called, they're little tubes that connect the outside of the cell with areas deep inside the cell. That's the T-tubular network. And those exist in working myocardial cells. They don't exist in Purkinje cells. There you have sort of a smooth sarcolemmal lining of those particular cells. So they're probably the most strikingly different interference. And AV nodal cells are different again, and SA nodal cells, they're a little harder to differentiate, but they're somewhat different in shape too. cells. So yeah, they have structural as well as functional differences.
As far as seeing them on a macroscopic scale, it's hard when you're just looking at the heart, but you can stain them. Something that's sometimes done is that you can wash the inside of the ventricle with a dye, and it'll preferentially seep into the Purkinje cells, and then you see like this spider web network branching out across in all directions. But as far as if you were to just look at a slab of heart, unless you really know what you're looking for, I doubt you could see it with your eyes.
Yeah, you wouldn't see Purkinje fibers.
Gotcha.
Even the best anatomist I ever saw gave a lecture in live dissect of the heart. He just kind of pointed to an area of the atrium and says the AV node is here somewhere.
Right.
Robin Ben said. Then we start with the ventricle activation from the Purkinje, and this is the start of the QRS. So as the ventricles fully depolarize, we get the actual contraction, and then as Ben said, then we get repolarization or recovery. We're not going to talk much about that still today because it's complicated. And then it starts over. So does anybody remember how we go about measuring this electrical activity? Eric, you're next. If not, we'll go around the room.
Well, like we talked about last time, you put leads, different positions around the heart to measure the dipoles from different directions.
Yeah, exactly. Do you remember what one lead set was called, where it has like the right arm, left arm, and the right or left leg?
I don't remember the name.
So it's called the Einthoven triangle. So it's the left leg. So yeah, so you create these, you put electrodes on each one, you create a positive end and a negative end. And then you can kind of look at which direction the electrical activity is occurring, and that will kind of help you define what your ECG looks like. So if you have a negative end and a positive end, and current is moving towards the positive end, what does the ECG look like, Tanner?
It's going up.
So ECG will go up. How about if it's going in the opposite direction? Figures.
Go down.
And then Anna, what if it is perpendicular to the lead?
It will stay horizontal.
So ECG remains in some baseline value. So that's a good chunk of what Jake covered last time, wrapped up into 15 minutes. So now I'm just going to tell you a few more leads that are involved in a clinical setting. So if we take this triangle, we can kind of do some trigonometry by adding in some resistors and doing some fancy math and create 3 additional leads that are used in clinical ECGs. Specifically, you have this one called ABF, where you're dividing the triangles vertically, ABL, which you're dividing them based on the left arm, and ABR, which is dividing them on the right arm. We don't really need to get into the specifics of how this all works, but just know that there are these leads as well. And then lastly, we also use these things called precordial leads. And these are used for specific diagnosis. And they function just like the lead, like the Einthoven and the kind of Einthoven additional leads, except for their reference to what's called a Wilson central terminal. And we don't really need to get into the meaning of that, but essentially it's an average of the Einthovens plus some fancy math, and it ends up being about 0, based at the center of the heart.
What was this lead set called again?
These are called precordial leads.
Precordial?
Mm-hmm.
Just want to make sure I heard it right.
Yeah, it's sort of the anatomical region, is the precordium, it's in front of the heart, I guess.
So they're positioned kind of right in front of the heart. They usually clinically, from what I know, I'm not a clinician, they're kind of based on where your ribs are located. That's how they kind of try and figure out the best positions for them. And just so you kind of have a reference to where they are on the heart. So V1 is really great at measuring activity on the right ventricle, and it can confer some information on the left ventricle because it has this like directionality component to it. So as it's activating along the RV, it's going to be going towards that V1 direction. Versus if the LV is activating, it's going to be more perpendicular or away from the V1 direction. So I know I just threw a lot of information at you. I'm going to continue to throw more information at you because we're going to look at some ECGs now. So this is what a standard ECG looks like. If you do it's normal, it's healthy. Just to break down what you're looking at, so lead 1, lead 2, and lead 3. So 3 additional Einstein leads that are nice and fancy. Right here you have V1, V2, V3, V4, V5, and V6. Those are the cordial leads. So you're looking at an individual section of all of them, and these down here are just longer rhythm strips of the leads. So you have V1, lead 2, which is the Einstein lead in V5. So,
Did you mention what the A leads were?
yeah, I just said that they're kind of math-based using resistors off the Einstein leads. I didn't get too specific into them.
Yeah, they're just direct algebraic manipulations of the lead 1, 2, and 3. And the A stands for augmented. So it's an augmented R, L, F as in right, left foot.
So it's not like an additional lead you're placing.
No, that's the thing to keep in mind. That even with the 3 apparently separate leads, they're also redundant. So you can construct one from the other 2. They come out of the math of in this case the Eindhoven triangle and the projections that they contain.
How many electrodes do you
Yeah.
guys think it takes to get all that information? Clinically, how many electrodes do they typically use clinically?
It's 10.
Okay, we got a guess for 10 then.
12.
Any other guesses? Okay, Ben, why do you say 12?
Well, because I've heard people talk about 12 lead ECG.
Okay, and Derek, why do you say 10?
Because I thought they put 10 electrodes for
Okay.
12 leads. But
So yeah, that's a little confusing. So it is 10. Right, so as Rob just said, 3 of those don't even require an electrode, right? ABR, ABL, ABF don't require an electrode in order to measure them. And then if we wanted to only do the Eindhoven triangle, we could just do 2. We would still need 3 electrodes, but you could reconstruct the 3rd lead from the other 2. But so if we exclude the ABR, ABL, ABF, right, that gives us 9 other signals to account for. But Derek said it's 10. Where does that 10th one come from?
This is the devious one.
What have we not talked about? Right, we're talking about all this electrical recording and equipment. And there's something that you always talk about when you talk about electrical recording.
the ground.
Yeah, it's the ground. And you just put it on the other foot. Right? Yeah, a little bit of a trick question, but
Yeah, it's actually even trickier than that because in a modern ECG card, it's actually what's called a driven right leg circuit, in the sense that you derive a signal. You know how do you do noise cancellation in headphones? Anyone know how that works? Okay, so that's the simplest way to get rid of noise is you record the noise and you subtract it from the signal, which contains both the noise and the stuff you're interested in. So all that droning from the plane, that gets recorded in real time, inverted and added or subtracted, however you want to see it, from the signal that's going into your ear is sort of getting broadcast. And before it gets sent to your ear, the noise gets subtracted away, so it goes to your ear, hopefully, is just a clean signal without the noise. And so the same is true with this driven right leg circuit, in the sense that you derive a signal from the other leads and send that to the body's surface through this 4th electrode. The net result being that all the measurement leads in the body are measuring a cleaner signal than they would because they've had the inverse of the noise added to it. It's very clever. There's a paper like IEEE transactions from the 60s or something that describes this idea that's been implemented ever since in any modern ECG system. So it improves the noise quality.
So, 2 more pieces of information, and then I'm going to have you guys do some math. Everybody's favorite thing to do. So we know, so you can see on there, there's these little pink boxes. There's actually boxes inside of those boxes, but just take a look at the, more clear ones. And each box is 5 millimeters. And then we know that for every 25 millimeters, that equals 1 second. So with these 2 pieces of information, as well as kind of looking at the ECG itself, how would you guys go about calculating the heart rate? It's a simple kind of conversion that all should have learned from fundies. Conversions never go away. So does anybody have any idea how to use, you know, these three things together to calculate heart rate?
A quick question that will help me understand that question more, and this might be dumb, but we have them listed like 1, AVR, V1, V4. That, but they're different leads. That's not time sequential, are they?
So they're all occurring at the same time. If you
Right.
want to look at more like continuous, you look down here. You
Okay.
want more than one, but this isn't a continuation.
Okay, that's
It's the same time.
what I thought. I
Yeah,
just
yeah.
wanted.
That's a good question. You can stack them all up
Yeah,
sort of
vertically.
vertically.
you do.
and time, they would be time, you know, if
Yeah.
it's done properly, they'd be all the time alike.
For this example, I would just pick one beat. We don't need to do any fancy averaging. Just pick. So, Lindsay, do you have any idea of how we go about doing this?
I'm forgetting the actual name, like when it's on a graph, but you would just look at like the same point on each cycle and like how many boxes it spans. Yeah, because then we could do rate over it was 25 millimeters.
Yeah,
Is one
so
cycle.
let's pick this one because it lines up nicely. So we see that we have 1, 2, 3, 4, and then a half. We can just round up to 5 to keep things simple. 5-ish boxes for one heartbeat. So how would you go from 5 boxes to beats per minute?
Box is 5 millimeters, you said?
Each box is 5 millimeters. Yep.
So 5 boxes is a second.
A second. Yep. Mm-hmm.
So that's how
Yeah.
heartbeat per second, right?
And then do that to beats per minute because that's usually what we talk about.
That would be from 60.
There you go. Does everybody understand how we got that? Just some kind of rules of thumb. This is what, Ravi has taught me in class, so maybe a different clinician thinks otherwise. James is not here to, tell me the current thing. But so a normal heart rate is between 60 and 100 beats per minute. If you're going too fast, this is a term called tachycardia. And if you're going too slow, this is a term called bradycardia. So now that we've talked about heart rate, everybody understands that, let's talk about rhythm. So Ben, can you annotate where the P wave is?
Yeah.
Maybe annotate a few, so people. Cool. Pick another one. Does everybody agree with Ben? Anybody disagree? Great. So you can see that depending on what leads you're looking at, the P wave is going to appear differently. So if you can't see it in one lead, I would highly recommend checking a different lead to see if it's a little bit more obvious. Sometimes they can be kind of obstructed by noise, but Derek, can you circle some QRSs?
Is that right?
Yep.
Another one?
Yeah, do one more. And then Tanner, will you circle some T waves? Okay. Cool. So this is how we're going to go through a bunch of additional ones. We're going to look at the rate, and then we're going to look at the rhythm. And then we're going to try and figure out what disease might cause a specific rate or a specific rhythm. Okay, Lindsay, will you circle some P waves? Or maybe, sorry, let's do heart rate first. Let's figure out what heart rate is. And walk through your process of trying to figure this out.
Nearly 7. So it'd be under 60 for the beats. I'm trying to figure out what it actually.
And people can help her as well. Yeah. I feel like this is a solo assignment. So if anybody else comes up with it. But you are correct that it's under 60.
Yeah.
But while you guys are figuring it out, sometimes we've got 2 regions, right? We've got the short signals, and we've got the long signals. And they serve 2 different purposes, otherwise they wouldn't be there. The short signals give us a snapshot of all the rhythms, all the morphologies. But then the long signals give us what it's doing over time, right? So calculating heart rate based off of one signal is a good starting point, but you also, once you have the heart rate in your head, you kind of want to glance down at the rhythm strip and be like, okay, is it constant or is it consistent? Do we have a number for 7 boxes per heartbeat?
43 beats per minute?
Great. So do we think this is fast rhythm, a normal rhythm or rate, or a slow rate. We're gonna, since you already did P waves, Tanner, you can do P waves.
Okay.
I'll switch lead here.
Oh, sorry. I'm on lead 2 on the bottom. The bottom says 2. Just
Yeah, that bottom thing's called the rhythm strip.
the rhythm strip. Sorry.
Great. Ben, will you do a QRS? Okay, so we have some QRSs, and then Derek, will you do some T waves? So does it look like it consistently goes P, QRST, P, QRST, or does it look like it maybe changes rhythm throughout? What do you think, Ben?
I think it looks pretty consistent.
Great. So if we have a slow heart rate and a normal rhythm, what disease do you think we would call it? And I told it to you when we talked about speeds.
Was it the bradycardia?
Yeah, exactly. So this one is called Sinus Bradychardia because you're in sinus rhythm, but your heart rate is slow. So now I'm going to go on to a new one.
Questions so far? This all making sense?
Okay, who hasn't calculated heart rate for me? I think Ben has. So Ben, go ahead and calculate that heart rate.
It's gonna be 120. I'm counting 3 boxes.
Sure.
And if we're saying 6 is 60, then double.
5 to 6.
5. Oh, 5 is, oh, whoops. 6 is, or wait.
Clever
6 would be
technique,
50.
though.
It's 100. It's 100. Yeah.
There you go.
Clever technique, though.
So is this slow, fast, normal?
Fast-ish.
Fast. We'll go with fast-ish. Have you drawn P waves, Lindsay? Will you draw some P waves? Or circles, sorry. You can draw some.
Just make them up.
Great. Who hasn't drawn QRSs or circle? Then circles and T waves. All right.
Is there any significance to that other than just it's just alphabetized and they
I
want
feel
to
like I
start
have to do something.
Well, there's other waves, other letters, but yes, it was alphabetical. That's
And it was Eindhoven who made the call.
It was who?
Eindhoven.
I told her.
and he was the first person to look at it.
Well, no, well, the ECG comes from the late 19th century, 1885 or so.
Wow.
Is there a reason they started at P and not like A?
I thought it was that he had like exhausted some other wave options, and he was characterizing the thing to death, and then they finally settled on like by the time they got the P, and things kind of shook out as what was real or not. Because there's also like the J wave and the U wave, and the like certain waves that come up, like in theory, come up if you believe in them during certain disease states, things like that.
Okay, so Derek, do you think we have a regular rhythm or an irregular rhythm?
Let's see. It looks pretty regular as well.
So then, Tanner, what do you think we call, maybe the disease state of this based on the rate rhythm we've decided?
Tachycardia?
Yeah, what comes before
Is
tachycardia?
it sinus tachycardia also?
Exactly.
Is there a different kind of tachycardia or?
We'll get there.
Okay, sorry.
Okay, so this one is going to be more complicated. I don't expect any of you to know the name of this, but we're just going to walk through what we're saying. Maybe we'll ask Jake or Anna, because they should know. Okay, Tanner, will you calculate the heart rate for this?
Yeah, probably. Okay, I didn't calculate. I think it's about 50. about 6 boxes, and we said 5 was 60, 5, 6 is 60.
That sounds about right. So do we think it's fast, slow, normal?
A little slower than 60, but it's not abnormal.
That sounds good.
They're in shape.
Yeah, they're doing well. Maybe they're an athlete or something.
Okay, Lindsay, will you do some P waves? I've asked you before, for practice. Great. Derek, do QRSs. And then Tanner, will you do T wave?
Mhm.
Okay, Ben, do you think this rhythm is normal?
Yeah, order wise.
Order-wise is normal. What's not normal?
The height of, well, the first thing that draws my eye is the peak of the QRS seems way taller than it should be.
Yeah, so when I said that, Robbie said we don't pay much attention to amplitude unless it's more so in the T wave, not so much in the QRS.
Yeah, the T wave's also height, isn't it? At least down
Yeah,
at B5 or,
don't worry about that.
okay.
What looks fundamentally different than shape-wise? If you look at D1, the QRS look normal.
It's not like,
Oh, yeah.
Wow,
It's like,
it's not
The T is
there's an inverted T.
What else is different?
QRS is, or
Is it the P the same as the QR?
I was gonna say, is the big spike a P wave, or is that just all QRS?
The QRS.
Ah,
So the QRS is
there's no
messed up.
P.
So
There's a P, there's P on other waves.
yeah, so
I
the
have
P
no
is
idea
there, but it's the QRS goes. There's essentially two peaks in the QRS rather than the standard one that we see. So, Anna, can you tell me what kind of disease? How do we go about figuring out what kind of disease this
So
is?
the QRS is wide. So I know it's a front branch block. So we look at the
Can
end.
you say what bundle branch block is first?
So pretty much the heart, like the electrical signal comes back normally on the left side, but on the right there's like a block, so it doesn't propagate normally.
Yes. So when you're talking about those His bundles, we have a left and a right side. Anna said that the left side's moving normal and the right side isn't moving normal. So it means that the left side is quickly activating and the right side is taking a slower time because it didn't activate those Purkinje fibers. So it didn't have that quick spread before it entered the working myocardium. So that RV is moving a lot slower. So how do we know that it's right versus left?
So we look at the end of the QRS. No, I'm gonna mess up. So if the end of the QRS is negative, it's right bundle, left bundle branch. So like in this like if we look right here, the last part is negative. So that would be a left bundle branch block. If it was the opposite, so like if the QRS was finishing like on the positive side, that would be a right bundle branch block.
So one thing that's a little different is you have to look at you pay attention to B1, not B5.
Right, left is positive or left is negative?
Left is negative
On B1.
on B1. B1 is the easiest to look at, and that's because go back to this right here. B1 is kind of really focused on that RV. So if you have this longer period of RV activation, that later spot's going to be moving towards B1. Versus if you have a longer time over here, it's going to be moving away from B1.
Okay.
So with that said,
That was mission critical. Did everybody get that?
Yeah, that's
Can you say one more time? The
so
the
if it's
moving toward and away.
towards B1, it's going to be positive. And since it's going to be positive later, that's how we're going to know it's right over the block. Because the left is already activated. activated. That's that sharp peak we saw. And that second kind of more wide peak is going to be the right ventricle activating. And if it's positive, it's because of this. Versus if it's a sharp peak and a negative wide peak, it's going to be left bundle branch block because the left ventricle is activating slower and it's away from V1. You can do this on different leads. There's nothing particular. All of them will kind of show a different thing. It's just going to be different directions. V1 seems the easiest. So, do we think this is right bundle branch block or left bundle branch block?
Left bundle branch block.
Look at lead one, or V1.
V1,
Or,
right?
sorry, lead one. Yeah.
Is the end of the QRS positive or negative? Negative.
Oh, sorry, I was looking at the T wave.
Positive. Yep. So then left or right? Yes. Does that make sense to everybody? Maybe? Well, we're gonna do the opposite side, so maybe that will help clear up the next.
Why is
So
the
do-
T negative on that?
T waves are a weird
Yeah.
phenomenon.
Don't,
Okay,
Don't worry
that
about
was
that.
true, yeah, but don't even look at it. Okay.
Well, I mean, not a wave, it's a phenomenon. And because some other stuff's happened, the ventricles are activating somewhat out of order, it's gonna change how the T wave looks in possibly difficult to predict ways.
Okay,
But the QRS is giving the clearest indication of what's going on here.
got it.
And like your heart, you know, if you think it, like, I find it helpful to have a physical bearing on your own body for where these leads would go. So right, the V1 is like right at about the nipple line on the right of the sternum, and then V2, and then it kind of comes down a little bit all the way to V6 in the mid-axillary line. And so your heart sits at about this direction, right, and it's a little bit off center. So that V1 is looking over here. So if you kind of think about, okay, activation is going to go this way, and then it's going to sweep up, right? But I'm looking at that QRS and I say, okay, it's going really positive at the end. So in order for that to be the case, I would have to have a bunch of activity going this direction towards V1 at the end, right? And it's wide, which means it's going slow, right? It's doing that for a long time, right? So that should tell you, okay, if the wave is going towards an electrode, right? Just remember, because Lindsay said these are all referenced to Wilson Central Terminal, so the measurement direction is from the center of the heart to the electrode, so that's the arrow. So if you project your major heart dipole onto that, it means it's going in that direction, it's positive, right? And so that means that it must be going to the right side slower at the end.
Any questions on that before I move on to the next one? So like we said, right bundle branch block, or it's abbreviated RBDB. Your leads, and I know we said it maybe had a little bit slow heart rate, but that's mainly because of this slower propagation over it. Okay, so now we have another one. Tanner, can you tell me the heart rate?
Yes. 60.
Derek, can you draw some P waves?
Sure.
They're a little bit harder to tell on this one, so just do your best.
Uh,
Okay, so Derek is marked as a P wave. They're a little bit harder to tell on this one, mainly because right here is a little bit noisy. You can kind of see it. So there's P wave, P wave, P wave, P wave.
Did we do heart rate on this one?
Yeah, Tanner did.
Okay.
Lindsay, will you do QRSs?
Not sure if it like would continue past there and go into that next.
So that next part is going to be the T wave.
Okay.
Well, I just told you where the T wave is, so we don't need to go over that. So do we? What is this left bundle branch block or right bundle branch block? So which lead do we look at if we want to make it nice and simple?
V1,
V1, okay, it's positive or negative.
negative,
So is it left or right?
left.
Does that make sense to everybody?
Someone describe it like physically, like what's happening, what's the wavefront doing?
So the later wave is going away from V1. So right.
if it is a left bundle, it's gonna go faster down the right first and slower down the left.
Okay, and slower, usually when we think about left bundle branch block, there's partial block, there's slowing, sometimes we think about it just off block. Okay, so if we follow it down the right, it's gonna shoot down the right, and the right ventricle is gonna activate, whatnot, it's gonna happen real fast. Okay, but then the left ventricle isn't gonna get that whole Purkinje network. Is it gonna activate? Yes, why? How?
They're still, the ventricles are still electrically connected to each other, right? So they still are gonna activate.
Right, from where? So where's that activation gonna come from? It used to come from the Purkinje, but now it's gonna come from where?
From the right side Purkinje, or I guess the right side ventricle that's gonna spread.
Right, so the right side of the heart is all activated, and that's just gonna slowly creep over to the left. Okay, and is the left bigger or smaller? Bigger. Okay, so that's more tissue that it has to do. So one, it's gonna be a bigger wavefront, more tissue, and two, it's probably gonna take longer. Okay, so now look up there, right? And that QRS for V1, you can't even see the right ventricle activating in there because the left ventricle is just so huge and slow and taking up the whole wavefront. Right? It's all negative all the time. Because in theory, we'd expect there to be a little positive bump as it comes over to the right side, but that happens so fast and it's so small compared to what the left ventricle is doing that you can't even see it.
I have two more examples, but before we get into them, I just kind of want to wrap up something just so we kind of have these. So Rob sent me one of these papers. Well, he sent me a title of one, and I found some other ones as well. That there are a lot of subtleties that can go into actually changing ECGs, such as stress when you're driving a car, diabetes, and even altitude. So there's a lot of changes in the ECG that are pretty subtle and not very unique that makes it to the point where it's not really tied to anything physiologically or anatomically. So these are some of the examples of kind of things that you get to use, like machine learning, to kind of help draw out some of the subtleties that aren't as clear as, the QRS is bigger or the P wave is gone versus, maybe a slight increase in the QRS amplitude. And it's just kind of good to know that this is still an active area of research. Rob sent me one that hadn't been published yet. It was preprint. So this is still actively being researched. So, it's kind of nice to know that things that you're learning about are still things that we are learning about. I don't know if Rob, you have anything to add to that?
No, I mean, the topic that's related to something we do a lot of is called uniqueness. So that's sort of a mathematical concept, actually. It's definition for a mathematical definition of it. What it practically means is that while every little change in the heart, or just about feels like every little change in the heart of any significance will change the ECG in some way that's kind of direct. And you could say, if this part of the heart tissue is inactivated, like a bundle blood branch, or even some smaller part of tissue is deactivated, that will cause some change in the ECG. And you can even map out that relationship. However, when you try from the ECG to determine which part of the heart is inactivated, then you get an ambiguous answer in the sense that multiple different scenarios in the heart can produce potentially the same abnormal features in the ECG. So there's not a unique mapping, that's another mathematical word, right? There's not a unique mapping between the features of the ECG and the underlying alterations or arguably features in the heart itself, which is what ultimately limits the diagnostic ability of anything. It's true across all kinds of diseases, right? You have a runny nose, your throat's a little sore, and you have a headache. What's wrong with you? You can make a long list, right? Could be COVID.
You want a list?
Yeah, exactly. Right? It could be a huge long list. So you have all these, and yet, when you have COVID, chances are very high these symptoms will occur. When you have a cold, chances are very high these symptoms will occur. So in that sort of forward, if you will, direction, things are, a little less unambiguous or, a little clearer. When you go in the other direction, things become very unclear. And so the process of diagnostics generally, certainly from ECG this is true, is kind of a process of elimination and saying, well, it can't be that because the QRS has a normal width. So it can't be a bundle branch, or it can't be slow conduction because everything is running in a normal time. The ST segment is flat, so it probably isn't, related to ischemia or Brugada or a few others. And so there's this long sort of logic tree that gets set up in a lot of medicine to try and identify diseases from these set of symptoms. And in our world, where we do this thing called ECG imaging, we're trying to get around some of those ambiguities to do the best we can from a body surface measurement to determine what the underlying electrical activity of the heart is. That problem is, again, ambiguous to some extent, and then the mathematical equivalent of that, or the physics equivalent of that, is the problem is ill-posed. So you'll hear us use that word, and it's nothing fancier than this notion that there's an ambiguous connection between the input to our system, the ECG, and the output to our decision-making, a cardiac abnormality, a localized conduction delay, a localized, some event that's abnormal or some event we want to localize in space. That connection is ambiguous. And so this ambiguity, this ill-posedness, those, they have conceptually the same thing. So don't be distracted, by the words. And just recognize that there is this sort of fundamental problem that, a lot of medicine has. That there's some you see somebody's two halves of somebody's finger poking out, it's pretty clear they've broken their finger. Right? There is some easy diagnostics like that. But a lot of the time it's a lot more complicated. And the ECG, while it's very cool how you can make these relationships, I have a block here in my Purkinje network and it causes this change in the ECG. That it is cool that there is that very clear relationship. But we have to be careful how we use it in the diagnostic direction.
Well, that's pretty much everything I had. So if anybody has any questions, we're here. But if not, have a great rest of your day.
Thank you.